Thanks, Kate, for the very nice introduction. So I share my slides. Can everyone see that?
Yes.
Okay. So so the talk is about evolutionary submodular optimization, and what I want to do is give you an overview on the area. So submodular optimization is a quite general field in the area of optimization, and there has been quite some work during the last 6-7 years, and quite a number of papers at machine learning, evolutionary computation, and artificial intelligence conferences. So you get basically my view on these things. And we also did a longer tutorial at GECCO this year, where you can find the slides in the ACM digital library if you're interested. All right, so let's see, hopefully that works. Just need to, okay, so I'm talking about evolutionary algorithms, and just that we are all on the same page. So evolutionary algorithms, when I talk about them, I see them as general purpose algorithms. You follow Darwin's principle, survival of the fittest. So, which means you're working with a set of solutions, which we call a population, but it's just a set of possible solutions to your problem. You have a parent population that produces an offspring population by some variation operators, such as mutation and crossover. And then after you've produced from the parents the offspring population, you select individuals from the parents and the children to create a new parent population. And then you just iterate the whole process until usually you've found a good solution. Okay. So the nice thing is that evolutionary algorithms, they are adaptive and they often yield quite good solutions for complex, dynamic, or stochastic problems. So the downside is that they are quite hard to understand what is going on essentially in terms of the optimization process, and it's not easy to analyze them. And there's a whole area on the theory of evolutionary computation that has built up essentially runtime results on evolutionary computation methods over the last 20 or 25 years. And the talk is somehow, it's a mixture on theory and applications, okay? So the motivation for us today is what we want to do. We want to understand a wide class of problems that evolutionary algorithms can solve or approximate well. And what I mean by that is essentially we would like to get theoretical results on evolutionary computation techniques that say, well, I get this approximation for that particular class of problems in this amount of time, right? And what we want to do is we want to consider submodular functions, and these are functions that allow you to model a wide range of important optimization problems. I will come to that in a minute. Let's look at the formal definition, and then I will give you an example, give you a bit more intuition on what some modular functions are. So you've given a ground set X with n elements where you have to select a subset of the elements, all right? And then a function is submodular if you have two sets A and B, if the union plus the intersection, the function values of that is bounded by the function value of the set A and the set B for all A and B that are subsets or equal of this ground set. So, so for me, it's easier to deal with an equivalent formulation of submodularity, and that is the following. So you look into a set A that is a subset or equal of B, where B is a subset of equal of your ground sets. Okay, so A is somehow included in B. And then if you add an element that is not in B, then you can't gain more than if you add an element to your set A. Okay, so that is a property of diminishing returns. You add it essentially to the larger set, and you can't gain more than you're adding it to the smaller set, assuming that A is included in B. Okay, and maximizing submodular functions is already NP hard. Okay, so important classes that are usually considered are monotone functions. So if you have a monotone function, then you can just add an additional element and you're not going down in terms of fitness. This doesn't hold for the general definition of submodularity, okay? So a function is monotone if you have a subset of another set, and then for the superset, the function value cannot be smaller. And we have a function that is symmetric if you're taking a set A, then the function value of A is the same as you're taking the ground set without A. Okay, so let me give you an intuition about submodular functions, and that is most probably the easiest thing to get a grasp of that. So that is the sensor placement problem. So you have an area that you would like to cover with sensors, and let's say a sensor is just somewhere in the middle and covers up to a certain radius. Okay, so now what you want to do, you want to select at most k sensors to cover the largest amount of area. Okay, so then the submodular property is saying, well, let's assume that our larger set is B and this contains all these red sensors. And we have a subset of A, of B, A that is considered essentially consisting of all the red sensors except for the one where you only have a B. Where you have when you have an A here, then this is a subset A. Okay, so now if you would take the set B and add X, then you can't cover more area than if you would take the set A and add X to that. Okay, and this is the property of diminishing returns. So A doesn't consist of this sensor that just consists of B. So if you would add X, you would get essentially this part here in addition, but you have this part already when you have selected essentially the set B. Okay. So now another example is MaxCut that fits into this definition. So MaxCut is just you've given an undirected graph and you would like to find a partitioning of the vertices such that the number of edges crossing these two partitions is maximal. So that's a classical combinatorial NP-hard optimization problem. And then if you just select a set of nodes A for the first partition, then this function just counts the number of edges that go between A and essentially the other partition of the nodes. So what you can see here is it doesn't matter whether you select A or V without A, so the function is symmetric. It's also submodular, so you're not gaining more if you have a superset already of A and you add elements, but it's not monotone, because if you are adding elements one after the other, then all the nodes get into the partition A, and in the end, you are not ending up with any edges between the nodes. Okay, and so what is important in that setting is also the set of constraints, and there are different types of constraints that you can consider. So one quite general thing is a matroid. So a matroid is just you've given a ground set, and you have a non-empty collection of subsets of your ground sets, and you have certain conditions that are fulfilled. So if A is in this collection, then any subset is also in that collection. And if you have A and B in that collection, but A is larger in size, then you can add an element to B that is not currently in A, but in that is not currently in B, okay, but in A. Okay, and the sets are called independent, and the rank is just of a matroid is just the size of any maximal independent set. So that is quite abstract, but it covers a lot of things. For example, if you've given a graph, then the ground and your ground set is the set of edges, and F is the set of all forests that you can have. So meaning just subset of edges that don't contain any cycles, and this is a matroid, and the maximal and independent sets are the spanning trees. Okay, and something quite simple in terms of a matroid is X is just a subset of, so you have given X and you consider all subsets of cardinality at most K, and we call this then a uniform matroid. All right. So, okay, so this is what you can consider in terms of constraints, and you will see that in many papers that they consider submodular functions in connection with matroid constraints or different other types of constraints. So let's go back a bit to submodular functions. What can you model with submodular functions? Of course, linear functions, where you just have elements and you just sum them up, the ones that you have selected. The class of linear functions fits in there. Cuts in a graph, I just explained that. Coverage problems as we had for the sensors, but you can make it more general. And also the rank of a matroid is a submodular function. Okay, so what this shows is that you can model quite a large number of problems using submodular functions. You can put in quite a large amount of different types of constraints. And now you would like to get essentially results for these type of functions in connection to the constraints. And so if you look into the literature of submodular optimization, not just particularly evolutionary computation, then the research in this area, you can characterize that by the functions that you would like to optimize. Okay, so one thing is, do you have a function that is submodular, or how close is your function to submodular? Is your function monotone or is it non-monotone? And you can take into account additional function characteristics that would then influence how well you can approximate essentially the problems. And in connection with your function that you want to optimize comes the types of constraints that you consider. So we can look into the uniform constraint as a simple thing, where you can select at most K elements. You can look into linear constraints like you have for the knapsack problem. You can have general cost constraints saying, well, I pick a subset of cities and I have a cost constraint in terms of how long my tour can be to visit these cities. Then you're getting already in the field where your constraints can incorporate something like the traveling salesman problem. And you can look into matroid partition constraints and any other things that you can think of. Okay, and most of the results that you see are of the form, so do we have a function that is submodular, close to submodular? What are the characteristics here? And what are the characteristics in terms of the constraints? And how well can we approximate that? Okay, so that's quite a lot. But what I want to do is I want to start now with something that is quite simple. Okay, and I would like to explain to you how these evolutionary algorithms work that have been analyzed in the literature, and what are the key ideas why you get these approximation results. Okay, so and most of the approaches that you see there in the evolutionary computation literature, what they do, they work with a bi-objective approach, meaning what you do is you formulate your problem as a multi-objective optimization problem. So the first thing is always, okay, so I would like to maximize my function value. So that's the submodular function that you're looking at. And the other one is, I have a constraint that I have to meet. So there's usually some cost on the elements, and there's a bound, and you cannot exceed that bound. So what this bi-objective approach is doing, it's trying to maximize the function value and minimize the cost value at the same time. Okay, and then you get trade-off solutions in the multi-objective sense. And what you try to do is really you're using an evolutionary multi-objective algorithm in the standard multi-objective setting. So you try to create trade-offs between the cost constraint and the function value, and essentially push it towards the Pareto forward. But in the end, what you're only interested in is the solution that has a maximum function value that is still a feasible solution. Okay, So for those of you who haven't worked that much in evolutionary multi-objective optimization or in multi-objective optimization, what you try to do is you try to push that one essentially towards the Pareto front. And if you look into a solution X, then these solutions up here, these are the ones that dominate X. So these are strictly better. And these solutions down here, these are the ones that are dominated by X. So if I have a solution X, I would reject essentially all these solutions that are dominated by X. But if I get new solutions that dominate X, then I would take such a solution and kick out X. So that's the basic idea here. Okay, so and what do you get out of the results? Usually what you get is that this bi-objective approach using these multi-objective evolutionary algorithms that enables the greedy behavior of the algorithms. And it also allows you to do local search and benefit from the interactions between the trade-offs of the solutions. Okay, so you're essentially working with a population here. You can add elements in somehow in a greedy way and create good solutions. You can do local search and improve solutions, and you can have interactions between the individuals. So now, from a theoretical perspective, you're getting a good approximation behavior for certain type of problems because you have this greedy or local search behavior. And I will give you 2 examples on that. So you get provable approximation guarantees. And in practice, you get the benefit of essentially greedy local search, the interactions, and this evolutionary behavior to give you good performance in practice. All right. Okay. So the baseline algorithm that is considered here in most of these analyses is what we call global simple evolutionary multi-objective optimizer. So what it does is it's working with this multi-objective formulation, and it starts with a solution uniformly at random. So you have a bit string of length n, which just means if the bit is set to 1, then you've selected an element, and if it's set to 0, then you haven't. You throw this first individual into the population, and then you have a simple repeat loop where you select an element from your population uniformly at random. You produce a new individual by flipping each bit with probability 1 on n. And if this new individual is not strictly dominated by any other individual in the population, then you add it to the population and you remove all individuals that are weakly dominated by a new individual from the population. So in this way, what this algorithm does, it keeps the set of all the trade-offs with respect to your 2 objectives in the population. Okay, and it also means that the population size may grow over time. Okay, so let me illustrate that on a simple problem. So what we would like to do is we would like to maximize a function f that is submodular and monotone here. And we would like to select at most, let's say, k elements. How would I do that? Now, what I would do is I would like to maximize an objective zx that equals just the function value of my submodular function if the solution is feasible, and otherwise it's getting a negative value. Here we assume that the submodular function assigns non-negative values. And the number of ones is just essentially going into the constraint. So I can select at most k ones, let's say, and then you're getting all the trade-offs between 0 and up to k. And what theory does is essentially when analyzing these algorithms, it's analyzing the expected time to obtain good approximations. And time in terms of runtime analysis of evolutionary algorithms is essentially the number of fitness evaluations that you have to do until you've obtained a good approximation. Okay, so there's what is not embedded is essentially the time to do mutation, the time to do selection and all that stuff, because in the black box setting, you assume that the fitness evaluation is essentially the most costly part. And if we have to run some simulations, then this is essentially the dominating factor. Okay, so now here's the setup for our maximizing the submodular function here with a number of elements at most k. Okay, so that's the setup that we saw before. So how it works in terms of greedy algorithm, at some point you're getting an empty set in there, and then you can add elements. This is often the path that you see in terms of the proofs there. Okay, so and what I want to show you is the first result is just saying, well, a solution is feasible if it has at most k elements. Okay, and then we would like to maximize a monotone submodular function. So, and we looked into that and essentially did a first step in this direction, did this together with Tobias Friedrich. That was a paper that we had at PPSN 2014 and then got published in a journal. And what it says, and the result is quite easy, is that global Zemo achieves a 1 - 1 on E approximation in expected time n squared k log n. Okay, so and it essentially resembles results from the end of the 70s that Nebenhauser and colleagues had in terms of a greedy algorithm. And I would like to explain this idea because you will see that in many other papers when you look into the literature. So what is happening here is you're getting the empty set in, and then if you would add an element that gives you the largest marginal gain, then it would construct these solutions. So the key thing is for element, if you have j elements, you are getting an approximation of the optimum. Okay, so xj is a solution with j elements that you get. That gives you something like 1 - 1 on k to the power of j. Okay, so and if you're looking into that, then if you would one additional element, then this j would go up to j + 1, and in the end, if you're at the bound k, the j would become a k, which means this term here becomes roughly a 1 on e. So, and then it gives you a 1 - 1 on e approximation here for the solution. That's essentially the standard idea that you also see in many greedy submodular papers and in many evolutionary computation papers. Okay, so what you need to fill in is essentially you need to run with this idea and then figure out what are the key steps that an evolutionary algorithm does. So what it will do is it would give you the empty set as the basis for getting a greedy behavior into your population, and you can bound this by n squared log n. I won't go into the details. And then you essentially get this greedy approach in, where you get for each j a solution with what I already explained in terms of approximation. And the proof to do this works with a key induction argument. So assume that you have already, up to a certain value of I, you have all these approximations for all values of j between 0 and up to I. Then what you can get is, if you pick the element with I elements and flip the bit that is currently not, not in this solution, then you get an increase that you can bound in terms of how far you are away from the value of an optimal solution. And that works because you're monotone and you're submodular. Okay, so what you get is you have an equation that says, well, the function value of an optimal is bounded by, I just add xi to the optimum, and this is bounded because of submodularity by what you already have plus k times the gain that you do. And then what you get is a gain for your step when you're adding the next element in, that is 1 on k times what is the difference between what you currently already have for your solution with I elements and the value of an optimal solution. And then you just put everything together by rearranging these terms and effectively just increasing the exponent by 1. So you would get an exponent then of I + 1 here for the last term. Okay, So this is just how it goes for this one. All right. Okay. So and then if this term up here in the exponent becomes the case, then you get a 1 minus 1 on E approximation for these things. All right. So the other one, and I just want to briefly touch on that, is when you're going away from monotone functions to non-monotone functions, then often the greedy stuff doesn't work that well, but local search still works quite well, and also for general settings. So if you're looking into the non-monotone symmetric case with matroid constraints, so you can have even k matroid constraints, and a feasible solution has to be in the intersection of all these independent sets, then you can also get results according to local search. So so we assume now that F is symmetric, submodular, and non-negative, but it's not necessarily monotone. Okay, so what can happen then? Then you can still build on the local search capability to get good approximations. And there's a result by Lee et al. That has been at Stock 2009 that essentially says, well, you can have local improvements where the local neighborhood that you have to search essentially depends on the number of matroids that you're looking at. Okay, so what does it mean for global Zemo? So for global Zemo, it means you're getting essentially the same approximation as it was there in expected time that depends on the parameters, but it's essentially also polynomial if the number of matroids is constant. Okay, so and I just want to highlight what is the idea with that. So if you go to global Zemo again, you're getting the search point, and I said that this is important, the empty set you're getting into the population after a certain amount of time. What you can do then is, if you introduce the element that gives you the largest function value for your problem, then because it's submodular, you're getting at least the value of op divided by n. Okay, and then the local search behavior says, well, you can flip essentially k+1 bits from your currently best solution and always increase the function value by a factor of 1 plus such an epsilon divided by n to the power of 4. So what does it mean if you essentially can increase the function value always by this factor? You can bound the number of steps that your evolutionary algorithm needs to get a solution where it can no further improve. And if it can no further improve, then the Lee results essentially tells you that you have obtained the approximation. So what it does is, so you need the number of local improvements is essentially the log, where you take the basis based on the factor that you can improve of op divided by n. Okay, and then you get essentially the number of improvements in. So it also gives you an approximation for MaxCut, although that's of course not optimal, but it gives you a result for MaxCut that you just get for this one here. Okay. Okay. So this was essentially things that were initial things that we looked at in 2014 and 2015, and then Xiaoyan and colleagues of him at Nanjing University, they did a lot of papers in the context of machine learning, more complex functions and problems and so on. And I won't go into details of these papers, but please look into our GECCO tutorial where he provided a lot of slides on these results. And he's also written a very nice book where you can find these results. What I want to do is I want to talk about problems that we became interested in during the last couple of years. So one is on dynamic constraints and the other is on stochastic constraints. So the one here, we presented that first at AAAI 2019, and there's now an artificial intelligence journal extended version that should be online, or at least it is on arXiv if you're interested. And what we've been interested in are problems where that are dynamic or stochastic, because they often occur in real-world situations. And often the goal function to be optimized is somehow fixed, right? So you would like to reduce costs or you would like to maximize profit. But the resources that you have, they are usually changing, and this sets the motivation for this work. So trucks or trains may break down or be repaired, and algorithms have to react to such changes that affect the constraints of your given problem. So what we want to do now, we want to look into evolutionary algorithms for such problems with dynamic constraints and get somehow results that are as general as possible in terms of the functions and the constraints that we consider. I will mainly talk about evolutionary algorithms and what is often then also called Pareto optimization. So that's essentially just the bi-objective model that I mentioned before. And then what happens for dynamic constraints. So let's look into what has been there before. So Xiaoyan with colleagues at GECCO 2017, what they did, they looked into quite a general setting that has been there, and a simplification has been considered in terms of greedy algorithms. So what you do is you look into a monotone objective function. So that's the only restriction on your objective function, and a monotone cost function. Okay, and you have a budget. So and the aim there is to find a solution that maximizes your function value subject to you're not exceeding the cost bound. Okay, so and what they got in terms of results is that you get an approximation phi that depends on essentially how close your function is to being submodular. So if this alpha f is equal to 1, then it's submodular. If it's smaller, then you're going away from being submodular. Okay, and the approximation is with respect to an optimal solution where you can somehow still calculate the optimal cost, because this cost here, in terms of a monotone cost function, that could include an NP-hard problem already. Okay, so it's essentially, this approximation is with respect to a reduced cost budget. So we took this setting and we said, well, okay, so what does happen now if this bound changes over time? What is happening then in terms of the behavior of our evolutionary multi-objective algorithm? Okay, so the dynamic problem is now, we assume that we have such an approximation as they had for the static problem, and the dynamic problem is just given by a sequence of changes where each change changes the current budget B to a new budget B star, and then the goal is to compute the same approximation quality for each newly given budget. Okay, and we said, well, if we are now using our this bi-objective approach where they showed that this works for the static problem, what does happen to the dynamic problem? Okay, we looked into that in terms of what greedy algorithms would do when you adapt this. So greedy algorithms here, if you have your initial budget constraints, they would just go for maximal gain that you can get with respect to the function value to the cost that you have to pay. And this adaptive one would then, if you're exceeding your budget, would just throw out elements according to this criteria or add new elements in. And I don't want to go into details because I want to concentrate on the evolutionary computation part, but effectively what it says that you can, if you're just doing that, then you get arbitrary bad approximations for even quite simple settings. And I'm happy to talk with you later about that, but I will just skip over these slides now and just tell you what you get for the evolutionary algorithms. Okay, so the evolutionary algorithm is essentially the one that we saw before. This is the global Zemo approach, but Xiaoyan named it a Pareto optimization, and this is standing here for constraints, but it's the same algorithm. it has the function value as one objective, as you see here. So if you're infeasible, then you're getting a largely negative value. And the other one is having the cost value here, where in the setting, you assume that you maximize both, but you can, I always think of maximizing the function value and minimizing the cost value. Okay, so, and let's plot this again. What you get, you aim to maximize the function value and minimize the cost value. So what they said is, if you have a fixed bound here, you get this solution that you get out of your evolutionary algorithm is a good approximation. So what we said is, well, if you run your evolutionary algorithm, you can pick any bound between 0 and the bound that you've set, and then your evolutionary algorithm for any possible bounds that you get between that will contain a good approximation. So if you would make dynamic changes now, decreasing the bound, for example, you would already have a good approximation for that newly given bound. And then the other thing is, if you would increase your bound, then for any possible bound in between that you could pick, you would also recompute a good approximation. And the runtime bound here is always dependent on, well, how many different trade-offs can you get? And if these costs and objective functions can take exponentially many values, then that could be quite large. And it also depends on what are the steps between the different solutions, essentially, how many steps you have to take there. But in principle, what it says is that this multi-objective approach caters for dynamic changes in terms of it would solve your problem and improve the solutions over time for all the budgets below that. And if you then extend your budget, you would also compute good solutions for larger budgets. Okay, so and what we did then, we looked into inference maximization problem, which is a submodular optimization problem. And we changed the budget over time like this. Let's say this is just giving you over 200 changes, how an example budget would evolve. And we gave the evolutionary algorithm certain number of time steps between a budget occurs. So 1000 means you have 1000 fitness evaluations until you have the next change. 5000 means you have 5000 iterations, and 10,000 means you have 10,000 iterations between the next change. Of course, if I give you a new budget, you can always run the greedy algorithm and you would also get the same approximation. And what we did, we compared then the greedy algorithm, which is this one, the GGA. This is the adaptive one where we showed that the approximation is not that good. And these are just the evolutionary multi-objective algorithms with 1000 iterations that you can do between dynamic changes, 5000 or 10,000. So what you see is that at the beginning, let's say for the first 25 changes, the greedy algorithm is better than what you get out of the evolutionary algorithms. And it's also better than the adaptive greedy algorithm. But over time, what you get is that the evolutionary algorithms improve in terms of their solution quality, and then they would beat the greedy algorithms that you have here. And that's the general picture. So you would need essentially some time at the beginning in terms of you're building up the population and learning about the problem, and then you're in a good situation afterwards. Okay. So the last one that I want to talk about is problems with chance constraints. So what we had so far were just static submodular problems. Then we had these dynamic problems where you change the bound. And now I want to look into situations where your constraint has stochastic components and you would like to minimize the probability of violating your constraint. Okay, so chance constraints, so the motivation is here. So you have stochastic components and you would like to violate your constraints only with a small probability. So let's assume now S is a potential solution to a given submodular problem. And WS is just the random weight or random cost, and B is a given weight bound. Okay, so we consider chance constraints here of the form that the probability that you violate your constraint bound B should be at most alpha, where alpha is usually a small value. Okay, so this is just the setting that we are looking at, and the other thing is essentially we would like to maximize the submodular function under this setting, and we assume now that the submodular function is again monotone. So the weight bound can only be violated with a small probability. So what we did then was to say, well, in general, determining this probability, what is the probability that your weight exceeds a given bound? That's already hard to compute. What we did then is depend on whether the items were independent and had same uncertainties. We considered either Chernoff bounds or Chebyshev's inequality. Okay, so and our settings essentially allow to look into both Chernoff bounds and Chebyshev's inequality because the uncertainty around each item was the same that was parameterized by an amount delta here. All right. So, but the other thing is, if you want to be very sure and alpha is very, very small, then you would prefer to use Chernoff bounds in that setting. Otherwise, if you're not that strict, then Chebyshev's inequality would give you somehow a better estimate in terms of this probability. So the upper bound would just be tighter for larger values of alpha when using Chebyshev. When you're having much smaller values of alpha, then you would like to use Chernoff bounds. And again, here's the global Zemo algorithm that we considered. And we did a multi-objective setup essentially that was saying, well, one objective is just the function value, the other is somehow violation in terms of the constraints. So you put the expected value on one axis, you're doing because we want to have small values of alpha. If you are above the expected value or above the constraint bound, then you give it a large value where you're not sure because the delta range requires that you evaluate this probability exactly. Then you use these estimates based on Chernoff or Chebyshev. And if you're sure that you can't violate the constraint, essentially, then you try to minimize the expected value. Okay, so now what does happen here? Again, we have this Pareto optimal setting. So you have the weight or the cost on one axis and the value here. And what we said, well, if we have deterministic constraints, then essentially we can go up to that bound and we are okay. So for the chance constraints, the process essentially stops earlier. So because you have the randomness around the expected value, you have to stop earlier to meet your criteria that you can't overshoot the bound with a certain probability. So, but the nice thing is then this gap here, in terms of what you lose, in terms of your constraint, that is not too big. Okay, so and the conditions based on Chernoff and Chebyshev, they say, well, if you're essentially this amount here, the square root of 3 delta k and so on, away from your bound, so your expected value is that by that amount smaller, then you meet your criteria in terms of the probability requirement. And you can get the same thing for Chebyshev's inequality. Okay, so and for what you can see is, well, you have the log of the alpha in here. This is why the log of 1 on alpha here. This is why Chernoff is essentially better when you need small values of alpha, where here you have essentially the alpha under the square root. Okay, so then what we get if the weights are all the same and have the same uncertainties around that, we're getting a generalization of the 1 minus 1 on E approximation. So you only lose a factor of 1 minus little o of 1. And you get the same thing essentially also for the case where you can have different weights, but then again, the population size can become larger, and you're getting a classical, essentially a 1/2 times 1 minus 1 E approximation, and you lose a small term little O of 1. All right, so I think what remains to be said is that we did some experiments with that, which essentially shows that the greedy algorithm is again outperformed by global Zemo. But surprisingly is that global Zemo is often also better than NSGA2. And especially when the constraint values become larger. So we did NSGA2 here with a population size of 20, which if the constraint bound is 20, then they are roughly the same. If it becomes larger, then the population has to be spread between all these different constraint values, and then NSGA2 is essentially losing the focus in terms of the good solutions. When we do this for more complex problems, and we have done some additional work that we want to submit soon, then we see that NSGA2 is performing quite well, and SPIA2 and so on, if you don't have uniform constraints, but you have general cost constraints. All right, so the same thing here for maximum coverage, essentially. Okay, let me perhaps stop here, and then we have a bit of time for discussion. So you can formulate many real-world problems in terms of submodular functions. So this is a quite general framework. And what you saw that you can have essentially bi-objective formulations in terms of your constraint on one end and the function value on the other hand, and then use evolutionary algorithms where global Zemo or POM-C, how it's often called, is giving you then the best possible theoretical performance guarantees and also giving you good performance in practice. And you also get this benefit when you're dealing with dynamic and stochastic constraints. All right. Okay. Thank you very much for listening.